Okay, all. Welcome to video class number 7, and we have already studied about the Fourier transform in video number 6. Now today, in this session, we are going to study about the properties of CTFT, and among that, the number one property is the linearity property. Now, what does this property states? So, suppose you have two signals, x1 of t and x2 of t as shown here, and whose Fourier transform is shown as x1 of omega and x2 of omega. Now, then the Fourier transform of a into x1 of t plus b into x2 of t will be a times x1 of omega plus b into x2 of omega. You don't have to use the mathematical expression to find out the Fourier transform if already you know the Fourier transform of these two. You just need to take the sum of that. So it will be, if x1 of t is multiplied by a, then definitely its Fourier transform will also get multiplied by a. If it is multiplied by b, that will be multiplied by b as well. So where a and b are constants. Now let's move on to the proof of this. So in order to prove this, we use this mathematical expression. That's the only thing that we have. So the mathematical expression is given by x of omega is equal to integral minus infinity plus infinity x of t e raised to minus j omega t dt. Okay, now instead of x of t, you will be replacing that by this a into x1 of t plus b into x2 of t. So that's written like this, integral. So it is replaced that into e raised to minus j omega t dt. That means this is common for these two. So you can split this integral as shown in this figure, as shown below. That is integral minus infinity to plus infinity a times x1 of t into e raised to minus j omega t dt plus b times x2 of t e raised to minus j omega t dt. Now here you can take a and b outside. That's what is shown here. And now what is this? This is actually the Fourier transform of x1 of t. This is actually the Fourier transform of x2 of t. So calling the Fourier transform, we have already assumed the Fourier transform of x1 of t is x1 of omega and x2 of t is x2 of omega. We can say that that is equal to a times x1 of omega plus b times x2 of omega. So thereby it is proved. Now that's it. Second property is the time shifting property. Now what is this time shifting property? Time shifting property states that say if you have a signal x of t whose Fourier transform is x of omega, we know what is time shifting. Time shifting is x of t plus say some tau or t minus some tau. We are taking it as t minus. So x of t minus t0. The Fourier transform of this is exactly the Fourier transform of x of t multiplied by e raised to minus j omega t0, where t0 is the shift element. So we can see that the only difference that we can see in the Fourier transform when that particular signal gets shifted is there is a presence of an exponential signal. So you can also have another view of this. That is, when you multiply a frequency, this is frequency domain, omega x of omega is a frequency domain signal. When you multiply the frequency domain by an exponential signal, that will result in time shifting. Hence the property is called as a time shifting property. Now we can have the proof of this. So when you start to prove it, this, you need to have again the basic mathematical expression. So the mathematical expression is shown as integral minus infinity x of t minus t0 e raised to minus j omega t dt. Now instead of t minus t0, you can put that is equal to p. So p is another variable, and since it is from minus infinity to plus infinity, you don't have to look for the range of p, because p also ranges exactly as, since it is minus infinity to plus infinity, exactly as t varies, p also varies. So when you differentiate this, you will get dt and dp. Okay, now from this you will be able to get t is equal to p plus t0. So doing this substitution here, that is t minus t0 can be substituted as p. Now e raised to minus j omega t can be substituted as p plus t0, and dt is substituted as dp. You will get the expression like this, that is integral minus x of p. Now you can from this you can split this exponential signal as this x of p into e raised to minus j omega p minus j omega t0 dp. We know that t0 is a constant, therefore this exponential signal has nothing to do with this integration, so you can take this outside, that is e raised to minus j omega t0 integral x of p raised to minus j omega p into dp. So this is exactly at, I told you that p also takes all the values of t, so it is equivalent in writing x of t into e raised to minus jt dp. When you say that, that we call as x of j omega. So here instead of t you have p, that's all, but p is exactly the same as that of t. It varies exactly as that of t. So therefore you can call this expression also as x of omega. So okay, x of omega multiplied by e raised to minus j omega t0. Now this is the time scaling property. Okay. Now from this you can also have this when you consider, if you are asked to find out the spectrum of a time shifted signal, what can you say about the spectrum? The spectrum is, say for example, the spectrum is actually the plot between modulus of x of omega versus omega and angle x of omega versus omega. Okay, you can have the plot in these two. This plot we call as, this is called as the amplitude spectrum, this is called as the phase spectrum. Now from this you can say that, so if e raised to minus j omega t0 is into x of omega is the new x of omega, that is if it is the Fourier transform of x of t minus t0, and the Fourier transform of x of t is x of omega. So when you take the magnitude of this, Fourier transform, we know that the magnitude of e raised to minus j omega is 1, that is it is equal to x of omega. So what do you infer from the regarding the amplitude spectra of such a signal? The amplitude spectra of such a signal is exactly same as the spectrum of x of t. Okay, so there is no change. The amplitude spectrum won't change. So we may be thinking, then what is the change in that? Yes, there will be a change in the phase. Now what happens when you check? So this is your x of omega. So when you take the magnitude, you are going to get exactly the same x, the Fourier transform of x of t itself. Now what about angle x of omega? The phase of the Fourier transform of x of t minus t0 will be, it is the phase of, okay, you can say that, say phase of what? Phase of e raised to minus j omega t0 plus the phase of x of omega, right? So this is a numerator. We know that if there is something like angle C into angle D, we can take the sum of this C divided by angle E. What you do is the net phase will be angle C plus angle D divided by angle E. So here you have only the numerator, that is e raised to minus j omega t0 into x of omega. So when you take the phase of this, it is the phase of e raised to minus j. What is the phase of e raised to minus j theta? It is minus theta. So similarly, what is e raised to minus j omega t0? This will be minus omega t0 plus the phase of, or the phase of x of omega, right? So whatever may be, so look at this, there is an additional phase of minus omega t0 along with the phase of x of omega. So what is the difference in the phase spectrum there? The phase spectrum differs. So these are the two aspects that you need to understand in a time shifting signal. That is, when a signal gets shifted, the amplitude spectrum remains the same, but the phase will be changing. An additional phase gets added up and it is equal to minus omega t0. Now when you look at this additional phase, you have minus omega t0, right? T0 is a constant. Okay, now omega is a variable, right? So angle of x of t minus t0, or rather the Fourier transform of x of t minus t0 is equal to minus omega t0, or you can say that this is proportional to the negative of omega, right? Negative of omega, right? So that means as omega changes, it is in proportion, right? So as omega changes, this phase also varies accordingly. So this is called as an introduction of, so by shifting you introduce a linear phase shift. Why linear? Because it is proportional to omega, right? So that is why it is called as a linear phase shift. So that you need to understand, that is, when a time signal gets shifted, the amplitude spectrum remains the same, while the phase spectrum will be having an additional linear phase shift in the form of minus omega t0. Hope you understood this. Okay, now the third property, which is the time reversal property. That is, in time reversal property, you have x of t whose Fourier transform is x of omega. Then you know what is time reversal. That is, it is the folded operation. So you will get x of minus t. X of minus t, it will be x of minus omega. So you can prove that. You can have the proof of that. So in order to prove that, you again use the basic expression, that is the Fourier transform of x of minus t is nothing but integral minus infinity to plus infinity x of, please note this is x of minus t into e raised to minus j omega t dt. Hope you are noting this in your notebook. You should have a notebook along with this while watching this video. So okay, so instead of minus t, you can put it as p. So you can take the dt is equal to dp, and we know that p varies from minus infinity, it varies from minus infinity to plus infinity, or again p also varies from in that direction. So it is again integral minus infinity to plus infinity x of p raised to plus j omega p into dp, right? By after having that substitution. Now from this, say you can take the negative. So you want to make it comparable with the Fourier transform equation. And what is the Fourier transform equation? We know that the Fourier transform equation is x of omega is equal to integral minus infinity to plus infinity x of t e raised to minus j omega t dt. So in order to make it comparable with this, you know that this is e raised to x of p is there instead of x of t. You have e raised to plus j omega p instead of minus. So how will you make it minus? You can take a minus outside. So when you take a minus outside, inside you will be having a minus. So okay, so that can be read along with this omega, right? So it can be read as j into minus omega into p. So now look at this expression very carefully. That's what I am going to say. So wherever you find the expression like this expression will be treated as x of omega, or in other words, you can say that this is going to be a function of the variable that appears along with jt, right? Along with minus jt. Am I right? Okay, so it is the variable. So that is why it is called as omega. And if you do that in this way, the variable, so this is going to be a function of the variable that is found along with minus jp. What is that variable? It is minus omega. So this is going to be a function of x of minus omega. Okay, so that is time reversal operation. Now so you can prove that the spectrum, when you draw the spectrum is going to be the mirror image of the spectrum of the original signal. Okay, so now the same operation will happen at the frequency. When a time domain is having a mirror image operation, the similar operation will take place in the frequency domain as well. That's the inference for this property. Now coming to the frequency shifting property. Now what is this frequency shifting? So instead of x of t, there will be a shift of x of omega minus omega 0 or omega plus omega 0. That's what is called as a frequency shift. Now, in order to have that frequency shift, suppose you have a signal x of t whose Fourier transform is x of omega, and you are multiplying that signal by an exponential signal, right? E raised to j omega 0 t. So that will result in x of omega minus omega 0. Okay, so how to prove it? Proof is simple. Again, you are using the basic expression. You are instead of using x of t, you are multiplying this x of t e raised to j omega t into e raised to minus j omega t. Since these two are exponential signals, you can combine that. So on combining, you will get it as minus infinity to plus infinity x of t e raised to minus j omega minus omega 0 t. Now, as I told you here, what will be this? This will be the function of the variable that comes along with minus jt. So if you go in that way, this is going to be a function that comes along with minus jt, that is minus omega 0, that is it is x of omega minus omega 0. Okay, now so you have found out that when you multiply the time domain signal by an exponential signal, that will result in time shifting. So we have already seen in this property, that is in the time shifting property. Okay, when you multiply this exponential signal in the frequency domain, that will result in time shifting, and in the frequency in the vice versa, that is when an exponential signal gets multiplied with the time domain signal, that will result in frequency shifting. Therefore, these two properties, that is the frequency, you must note here, I haven't mentioned anywhere on this slide, so you should note this, that is the frequency shifting property and time shifting property are called as one of the dual properties. Okay, so please note frequency shifting property and time shifting property as are duals. Okay, now you have the time scaling operation. Now what is time scaling operation, right? Time scaling is nothing but if you have a signal x of t, time scaling is x of at. Okay, or it can be x of t by a. All these are called as time scaling, and we are just considering it as x of at. And the transform of this is going to be x of omega by a into 1 by modulus a. Do remember that? So when you have at, that is when time, this is called as time compression. Time compression will lead to frequency expansion, omega by a, and this itself proves the time frequency inverse relationship. When time is compressed, when time is compressed, frequency gets expanded. So what is the reverse statement? If time is expanded, then frequency has to compress. Okay, now to prove this, so I'm considering again the basic equation f of at is equal to integral minus 20 x of at into e raised to minus j omega t. Again the simple substitution method, at is put to be is equal to p. So here also p varies exactly as t varies from, so t is equal to p by a. Make those substitutions here. After making the substitution, you can write this Fourier transform of this is equal to x of p into e raised to minus j omega p by a into, instead of dt you have dp by dA. So you're substituting like this, dp by dA. Okay, so this is equal to 1 by a. You can take this 1 by, this a is a constant, therefore this 1 by a can be taken outside. Integral minus infinity to plus infinity x of p, this is x of p, there is no a, this is nothing. Okay, x of p into e raised to minus j omega p dp. Right, now what is this? This is equivalent to what? Again, when you look at that, say instead of minus jt you have minus jp, so it is going to be the variable along with minus jp. What is that? It is omega by a, so it is going to be x of omega by a into 1 by a. Now in this case we are just considering it as a is positive. Now this is also valid for a is negative. If a is negative also, you are going to get 1 by a, that you can the proof is given in the textbook, you can refer for that. So that is why we use a modulus a. Whatever may be the value of a, whether it is positive or negative, this is going to be 1 divided by modulus a into x of omega by. Okay, now you have next property is differentiation in time. That is, what's the meaning of differentiation in time? So you have a signal x of t, right? Okay, now when you differentiate this with respect to time, this is also another signal, another time domain signal, say y of t. So if you know the Fourier transform of this, Fourier transform, say let it be x of omega, you can very well find out the Fourier transform of the derivative of that function. You don't need the mathematical expression for that. That is what this property states. Now let us see what is that. So if you have the Fourier transform of x of t, x of omega, then the derivative function, the Fourier transform of the derivative function is, it is j omega times x of omega. So it is just just multiply your x of omega by the term j omega. Now how is it proved? Now in order to prove that, there is a slight difference in the approach. So far we have used the basic expression of x of omega, that is the Fourier transform equation. Instead of using the Fourier transform equation, in this, that is the first thing that you should note here, the difference between other proofs from the other proofs. That is, here you are going to use the inverse Fourier transform, or that means the if you know x of omega, you can very well find out x of t. That is called as an inverse Fourier transform. So this is x of t is equal to 1 by 2 pi integral minus infinity to plus infinity x of omega e raised to j omega t d omega, right? Now we want to find out dx of t by dt. You can straight away differentiate this operation. Now this differential has nothing to do with, when you differentiate this on both sides, this differential has nothing to do with x of omega. X of omega remains a constant with respect to d omega. That means this thing is not, there is no omega, so this is with respect to time. So but inside this you have an exponential signal. You can take the derivative of that. So it is d by dt of e raised to j omega t. We know the derivative is with respect to time, so it will be e raised to j omega t into j omega, so that you can take the j omega outside. That is j omega divided by 1 pi integral minus infinity to plus infinity x of omega e raised to j omega t dt. Right. Now you can combine this j omega as j omega into x of omega into e raised to j omega t d omega 1 by 2 pi. So this is actually the derivative of x of t, right? When you take the derivative of this. Now, what can you say about this signal? That is, this can be written as, okay, when you take j omega outside. Okay, now look at this expression. This is actually again a time domain function. So you can call this as, say, some y of t, or you can write this as some y of t. So this is another inverse, 1 by 2 pi into integral. What do you do for this? So this is actually, okay, j omega into x of omega. Okay, so what is this y of t? Y of t is the derivative of x of t. We know that this is the derivative of this function. So this derivative, now you are actually finding out this as the inverse. So from this you can say that this is going to be the Fourier transform of this inverse, right? Y of t. Say, look, in this expression, what is this x of omega? X of omega is the Fourier transform of x of t. So from this you can say that j omega into x of omega is going to be the Fourier transform of this. Okay, so that's what is written here. So what about the nth derivative? If you have n derivatives, then that will be j omega the whole raised to n into x of omega. Now, next is the differentiation in frequency. So what is the impact of differentiation in frequency? Now you can say that, say suppose you have a signal x of t. This is the Fourier transform of x of t, may not be legible as always. So this f of x of t, it is x of t, it is given as x of omega. So you need to take a note of this. So I'm just multiplying this x of t by the time variable. So there will be a Fourier transform for that. So that is, here what I'm doing is, say I have an x of t signal, I am multiplying this signal by x of t. So the Fourier transform is x of omega. What is the impact of multiplying this t by x of t? So from this, you are again using this basic expression of finding out the Fourier transform. This is equal to x of t into e raised to minus j omega t by dt. Now what happens? So in this, the procedure is you will take the derivative of x of omega with respect to omega. So when you multiply this t, x of t by the time variable, the procedure is write down the basic equation of x of omega and take the derivative of this. Now when you take the derivative, integral minus infinity to plus infinity x of t e raised to minus j omega t dt, you are taking the derivative of this, right? So when you take the derivative of this, x of t is a constant, while it will be deriving this e raised to minus j omega t. When you take the derivative with respect to omega, jt is a constant, minus jt is a constant, so this will be jt dt and minus. Okay, now you can take this minus j outside, so integral minus infinity to plus infinity t times x of t e raised to minus j omega t dt. Okay, now so this is, so this you can say that what is this? What is this? This is t into x of t e raised to minus j omega t dt. This is equivalent to x of t into e raised to minus j omega t dt. So this must represent a Fourier transform. Fourier transform of this signal. So this is minus j into the Fourier transform of t into x of t. So what is the Fourier transform of this? So you have minus j into, so you have minus j into the Fourier transform of t into x of t is equal to what? Equal to the derivative of x of omega by d omega, right? Now what will be f of t into x of t? You can, so this will be 1 by j, 1 by minus j into derivative of x of omega by d omega. When you bring this j up, so it will become plus j. Okay, so this will be plus j d of d omega of x of omega, right? So okay, so these two property, that is differentiation in time and differentiation in frequency, can be considered as a dual in a way that, say, this is actually omega times, even though there is j, it is omega times x of omega. That means you are multiplying your x of omega by its frequency variable. That results in time domain differentiation, right? Now similarly, when you multiply your x of t by the time variable, that results in the derivative in the frequency domain. Therefore these two properties are duals again. Now this differentiation in frequency, in some textbook sometimes it may be called a t times property. T times property, you make a note on that as well. T times property. Okay, now you have the property number 8. Okay, you have property number 8. Now in this property, this is called as a time integration, and it is nothing but, say you have x of t, you have a Fourier transform x of omega, right? If you integrate this, this is also going to be a time domain function. That means that must also have a Fourier transform, and the Fourier transform is given by 1 by j omega into x of omega plus, it is plus. Okay, just note this, this is plus, this is not into, this is plus pi into x of 0, capital X of 0 into del of del of 0. Okay, it is del of, it is not del of 0, del of omega, del of omega, right? Del of omega. Now, so what is this x of 0? Capital X of 0 is x of omega at omega is equal to 0. Del of omega is, what is del of omega? Capital X of omega is x of omega at omega is equal to 0. Del of omega, by del of omega what we mean is del of omega d omega will be equal to 1 at omega is equal to 0. That's the meaning of that. Okay, now we are going to the next ninth property, which is the conjugation property. Okay, now what is this conjugation property? What do you mean by conjugate? So if you have a signal x of t whose transform is x of omega, right? X of t is, now this is called as conjugate. When the conjugate will come into play, when this x of t is a complex signal, that is, it is of the form a plus jb, then a minus jb is called as a conjugate of that signal. So that is represented by x star of t. Okay, now x star of t. Now let's have a look at this. Now if you have the conjugate x of t is equal to x of omega, then the Fourier transform of x star of t will be x star of omega, but omega is to be replaced by minus omega. You can have the proof of that. So again, starting from with x of omega, you have x of t into e raised to minus j omega t dt. Now starring this, starring means taking the conjugate. So if you have x of t as a complex signal, then x of omega has to be believed as a complex this thing. So x of omega, obviously that is a complex quantity, so there will be some x star of omega. So what will you, so star always refers to the conjugate. So you are going to take the conjugate of this whole expression. This is all raised to conjugate. So this will be, now putting the conjugate inside this bracket, you will get minus infinity x star of t e raised to minus j omega t. We know that e raised to minus j omega t is again a complex number. So that is also of the form, so e raised to minus j omega t is cos omega t minus j sin omega t. So its conjugate will be cos omega t plus j sin omega t. That means there will be only a change in this sign. So the change in the sign will denote the conjugate. So this is x star of t into e raised to j omega t. Now, what must be this? So x star of minus omega. When you say what will be x star of minus omega? X star of minus omega will be E is equal to x integral minus infinity to x star of t e raised to minus j omega e raised to minus j omega t. Meaning, if you want to put a minus here, you should also put a negative here, right? So again, look at that. This is going to be what? This is going to be right. What is this? This is x star of t into e raised to it is, this function is going to be a variable that comes along with minus jt, that is, it is minus omega. So this will be x star, this is x star of omega, x star of minus omega. Okay, so or it is actually the Fourier transform of this x star of t, right? Okay, next is the convolution property. Okay, convolution property. What is this convolution property? Say you have say two signals, x of t and h of t, right? So whose Fourier transform is x of omega and this one is h of omega. Now you know y of t is nothing but y of t is x of t star h of t, or this is actually equal to minus infinity to plus infinity x of tau into h of t minus tau t tau, right? Now what is this y of omega? Y of omega is going to be, you are integrating from minus infinity to plus infinity instead of x of t, right? Or what is y of omega? Y of omega is nothing but it is y of t into e raised to minus j omega t dt, right? So this will be integral minus infinity to plus infinity. Instead of y of t you have again you put one more integral from minus infinity to plus infinity x of tau into h of t minus tau d tau, the whole into what? Then comes e raised to minus j omega t dt, right? Now you can put t minus tau is equal to what? T minus 2 is equal to p, or dt is equal to dp. Here also p varies from exactly as t varies. So you can write this as, so you can have two integral together, minus infinity to plus infinity, again minus infinity to plus infinity, x of tau into, what is t minus tau? T minus tau is h of p into e raised to minus j omega t. Instead of t, you can, from this you can write the t as p plus tau, right? So you can write this as p plus tau into what? Into d tau, and dt can be replaced as dp, right? Now okay, now you can take this, from this integral you can take x of tau and d tau to one of the sides, say minus infinity to plus infinity, x of tau into d tau, right? There's no problem in that. Then you have the integral, next integral minus infinity to plus infinity, h of p into, it is simply a rearranging, e raised to minus jp into e raised to minus j omega p. I am taking one exponential outside, so it will be dp, okay, dp, this is all into, I am taking what? E raised to minus j omega tau, e raised to minus j omega tau outside. Okay, now what is this? So integral h of p into h of p. So it is similar to integral minus infinity to plus infinity. What is it? X of x of t into e raised to minus j omega t dt. Now you can rewrite like this, integral minus infinity to plus infinity, x of tau. I can bring this e raised to minus j omega tau into d tau into integral minus infinity to plus infinity, h of p into e raised to minus j omega p into dp. What is this? This is it? This is actually the x of tau. Instead of x of t, it is x of tau into e raised to, so this will be x of omega, right? This will be, so this is like this, into what is this? This is h of omega. So this is h of omega, right? Y of omega is equal to x of omega into h of omega. So this is the convolution property. Now let me explain some more about this. You in that frequency domain, you have the multiplication. Two signals got multiplied, x of omega into h of omega. That results in what? Time domain convolution, x of t star h of t. Now what is the use of this property? So you, as we have done some problems in convolution, it is found out that it is a bit complex in the time domain. So what you need to do is convert that convolution into its frequency domain. So in the frequency domain you just need to do what? The product of that, x of omega is to be multiplied by h of omega, and in order to get y of t from y of omega, you just need to find out what? The inverse of this, just as we studied in Laplace transform. So that is the power of this power. So this is a very powerful property, convolution property. Okay, now similarly, there are some more properties. Say you may note that as multiplication property and autocorrelation property. All these things you may just refer the textbook, and you may note down those properties, the results of those properties. So altogether you have, I think, about 13 or 14 properties. Okay, now in this the last section under the property is the Parseval's relation. Here also you have Parseval's relation. Parseval's relation for this, we usually say this is for the aperiodic signal. Aperiodic signal, right? Now we have seen such a relation in the periodic signal. and we have seen that the power is, we have found out an expression for power which is equal to k is equal to minus infinity to plus infinity modulus of ck square. Similarly, here in Parseval's relation you will derive a energy relation. Okay, we'll start with the energy signal. So before that you need to assume that x of t is Fourier transform of the x of omega. So we are going to find out an expression of energy in terms of x of omega. Since x of omega is a continuous function, there no longer there will be a summation. Instead of that, you will be having an equation where there is an integration. Okay, now let me just write down the Parseval's relation. What is this Parseval's relation? It relates the energy, or it gives you an energy equation. And we know that the time domain equation is nothing but it is the modulus x of t square dt, which we have already studied. Now the expression for energy can be found out to be 1 by 2 pi integral minus infinity to plus infinity x of omega modulus x of omega square d omega, right? So you can use this expression also to find out the energy. You don't have to find this expression. You can also use this frequency domain expression to find the energy. So at that, in the case of a periodic signal, we call that as the power density spectra or power spectra. Okay, now the resulting, so this resulting spectrum which we are going to derive here is going to be called as a energy density spectrum. Okay, I will explain what it is. So basically the energy equation, we know that it starts from x of t integral minus infinity to plus infinity modulus square dt. Okay, now this is equal to integral minus infinity to plus infinity. X of t has to be assumed as a complex signal, so it has to be, this can be written as modulus x of t can be written as x of t into x star of t dt, right? Now this dt. Now see this x of t, I'll talk about something about x of t. What is the basic expression of x of t? That is the inverse of Fourier transform. That is 1 by 2 pi integral minus infinity to plus infinity x of omega e raised to j omega t d omega, right? So what must be x star of t? X star of t means you are taking the star of this. You are taking the star of this means minus infinity to plus infinity x of omega e raised to j omega t d omega, right? So you are taking the star of this. So this will be 1 by 2 pi integral minus infinity to plus infinity. Bringing the star inside this will lead to x star of omega. And as I've told you, this is e raised to j omega t is again a complex number of the form cos omega t plus j sin omega t. The conjugate will be minus. So that means you just need to put a minus sign here to find the, so this is minus d omega. Now, so instead of this, you can write this as minus infinity to plus infinity x of t into 1 by 2 pi integral minus infinity to plus infinity, okay, x star of omega, right? From this x star of omega into e raised to minus j omega t d omega, right? Okay, now okay, now this is equal to, so this is equal to okay, you have this so you can write this as, say, integral minus infinity to plus infinity. You can bring this together, x star of capital X star of omega into d omega there. Okay, bring 1 by 2 pi outside, and it is just a sort of rearrangement, that is minus infinity to plus infinity. Take x of t, right, and e raised to minus j omega t, right, minus j omega t. Then here you have a dt here. Okay, I forgot to write this dt. So this will be into dt. So that is x of t into x star of t dt. So you need to put a dt here. So that dt. Now what is this? This is again the relation for x of omega, right? So This is 1 by 2 pi integral minus infinity to plus infinity x star of omega, okay, into what is this? The whole thing. The whole thing is going to be equal to x of omega and this d omega, right? So what is this? This can be written as 1 by 2 pi integral minus infinity to plus infinity x of omega modulus square d omega, right? So this is the energy equation. So you don't have to use this equation. Even if you don't have x of t, you only have the spectrum of the signal, that is x of omega. You can find the energy of the signal by using this expression. So you can have a plot of x of omega versus x of omega square versus omega. And previously you have studied the plot of x of omega versus omega is said to be the spectra, and from that you can have two spectrums, that is amplitude spectrum and phase spectrum. If you draw x of omega square modulus x of omega square versus omega, since this denotes the energy, this is a spectrum. The spectrum is called as a energy spectrum of the signal.